that the motion on a straight line with a constant acceleration a initial velocity v naught and the initial displacement x naught.
All right. So I have 3 questions. Hey. All right. Once your phone, you make all kinds of weird noises. All right. So where am I at? Which section are we at?
5.1.
5.1. Number, which one?
19 and 22.
Oh. Okay. They do an example. Let's see. We're going to get deeper into this. All right, guys. So I like this question because it gets us into what we're going to do today. 5.1, number 19. The whole little section, 19 and 22. Well, 22 is from a different section. 22 is just the reverse of 19. The area under a function from x equal a to b. So I have some function, and I want to know the area from a to b. Okay. So that's what we're focusing our attention on at the beginning. That is given by, now we've seen this before, where we break this up into rectangles. I'm going to break it up into end rectangles. So there's a width to it, and there's x1, x2, x3. I just call it xi for in general. Are we all good? We did that concrete example last time. Oh, we still got to finish off that handout, right? I think we do. So we have this sum equal 1 to n. I want to add up all the areas of these rectangles. So if I call A x1, x2, x3, this is xi. I want to make sure you guys are with me. And if I use, it doesn't really matter in what we're about to do. It doesn't matter which side. It doesn't even matter if you just pick an arbitrary point in the rectangle itself to designate the height. Because if I let the number of rectangles go to infinity, who cares which point I pick? Because eventually I'm not going to have much choice. Right? Does that kind of make sense? So it really doesn't matter on the way to infinity which point you choose to pick. Because basically when you get to infinity, you ain't got no choice. I don't know if you guys are semi with me or not. Because there are ways to do random choices for what your height is. We did left endpoint, right endpoint. We talked about the midpoint a bit. We averaged the right and left endpoint, that kind of thing. All right, you guys are semi with me a little bit. All right. Let's see. So then we have the height, which is designated by the function evaluated at xi. Right? How we do it so far? It's the height of the rectangle times the width. Hello. And if I, to make this equal, this is approximately equal for any finite n. So to make this actually equal to the area, I make my resolution basically infinite, right? Gamers go, what? Yes?
There are some problems that, like, they don't give you A or B, and they just give you N. So, like, how would you find the width?
You tell me which problems those are, and we'll see what's going on there, because I don't believe that. Is that cool? Right? And then we make the connection. We actually replace this, all this mess of symbols here, we replace it with this. Alright. So today we're going to focus on actually doing this by hand. Oh, joy. This is sort of like doing limits before we knew the shortcuts for derivatives. Right? And people are like, why do we do that? Well, probably so that you have some kind of idea as to what they really are doing. Right? I don't know. The main idea here is to learn. I don't know. Okay. So, all you got to do now is fill this in. For number 19, they give you a function. They say f of x is 2x over x squared plus 1. They want to go from 1 to 3. Blah, 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 blah. How deep did they get into this? Let's see. They got a little bit into it. Okay. All right. I like it. So let's try it. All right. This is going to lead us into today, pretty much. Let's try to figure out what each of these pieces are. Well, this one's easy. Not really yet, because I got to figure out what this is. And to figure out what that is, I actually have to first figure out what this is. So, what I want you to realize is, this piece, this limit piece, is, I'm going to throw that on after I figure out everything else. Everything's going to be dependent on n, and then I'm going to let n go to infinity. So don't let this part freak you out. Let's see if you guys were with me. What was the formula for delta x? What was that formula?
E minus A.
So what's that? For this specific problem?
3 minus 1 over there?
Yeah, 3 minus, yeah, so 2 over n, right? How are we doing there? Cool. So if you took 8 rectangles, they would have to each be 1/4 wide, so they would fit from 1 to 3. Let that sink in. Is that cool? If I had how wide is this area that I'm interested in? 1 to 3, it's 2. So if I wanted 8 rectangles, they have to be 1/4 big to all fit in there, right? That's exactly what it is. So how many will I eventually want? Infinity, but don't worry about that yet. You don't have to worry about to set this up. That would be a last step. So that's delta x. Now somebody help me out. What would x1 be? Let's use, just to make this easy, let's use left endpoints. Alright, so let me make sure you guys are with me. So roughly, what does this thing look like? Who cares what it really looks like? But it goes from 1 to 3. Here it is. So what's x1 going to be? Don't overthink it. I'm not talking about any area. I'm just talking about what's going to show me what my first height's going to be. Well, that's going to be the height. So what's the actual input is 1. Now what's x2 going to be? This is where things get interesting. How do I tell how far to go to find the next side of the next rectangle? What about 2 over n? Something about that. Because how wide is this rectangle? 2 over n. So if I start at 1 and I go that much, I get to the next thing, don't I? So what's the next 2 going to be? Alright, good. And what's the next thing going to be? No. Now I start at 1 and I go, how many steps? How many of these? 2 of these. So I want 1 of them here, right?
So, could you just say delta x plus 1 for the f of x thing right there?
Where am I at?
For the f of x of I, could you just put that as x of I plus delta x for the change?
No, well, no, because it depends on what a is.
Okay.
Right? It's a plus delta x, really.
Okay.
Yeah. Oh, let me see where I'm at. Okay. I'm going to try to merge this with what we're doing later. Well, I could use right endpoints, I guess. It doesn't matter. If I would have used right endpoints, which might have been a little bit better. Let me think about this. I'm trying to merge this with later. Yeah, I guess this will merge better. Because it really doesn't matter at the end which one we use. Let me make this xi. Hi. Alright. Okay. Let me see you guys with me. Really deep breath. So the next one would have been 1 plus 2 over n. x2 would have been 1 plus 2 over n times 2. x3 would have been 1 plus 2 over n times 3. You guys see why I'm doing that a little bit? It's this notation that they think the first thing is 1. If the first thing were 0, a lot of our troubles would actually go away a little bit. Well, I'm trying to match these up so it's a little bit easier pattern to deal with. So what's xi? It'd be 1 plus how many of these? I of these. So there, I've just switched over to right endpoints for this, just to make it easier to see the pattern. So please understand what's going on. The first rectangle is either going to start at the first number, or it's going to have a height determined by the next thing over. right? It's going to be either left endpoint or right endpoint. That's the main things you're doing. You could use midpoints too, but it makes this formula get really kind of gross.
Is the 2 over n the height?
No. What's the 2 over n? That's the width. The height changes because the height, of course, is determined by what the function is doing.
Right.
So this piece here is the height. This piece here is the width.
Okay.
So that I can see my rectangles and adding up my rectangles areas.
Is that why you're doing 1 plus the whole?
So now what I'm doing is I'm trying to figure out, since I'm going to want to eventually use infinite number of rectangles, which I really don't want to write them all out. It would actually be basically impossible for me. What I'm trying to figure out is a formula for seeing what the form is of each height of each rectangle. So in this one, if I go A, this would be A plus delta x. This would be A plus 2 delta x. Is that cool? Because the first rectangle would be there, there, and so forth. Blah, blah, blah. Until you get to A plus I delta x. And then you eventually get to B. And then get the full area underneath. Okay, cool. So I want to figure out, based on this little subscript I, this guy. Because that's what's controlling how many rectangles I've got. So I want a formula that tells me what each of these are. And what's going to affect what each of these are. It's going to affect where it starts. It's going to affect by A. It's going to affect it. And it's also going to be affected by how wide overall this is. Right? So this comes into play, obviously. That's what delta x is. And then now xi is going to be starting at A. It's going to go up by this much to get to the next part of that rectangle. Right? So start at A, and I go up by a width to get to the next. So this will be x1. This is x2. This is xi. Stay with me. We're still doing areas of rectangles. What's important for each rectangle, though, is the height. Well, how do I figure out how tall it is? I have to figure out what to input into the function, because the function tells me how tall the damn rectangle is. So if I don't know what to input into the function, I'm screwed. Hello. So that's what xi is. That's what this guy is. What am I going to put into each function to see how tall it is for that rectangle that I'm at that moment, and then move to the next rectangle. So this is me moving from one rectangle to the next, to the next, to the next. These are the inputs I'm going to use to see how tall each one is. Okay, maybe. So this is nothing different than what we did the other day. It's just more abstract, which students think of as different, and math people just think of as more general. Right? It's the same damn thing we did the other day, just more general. All right, so let's see where we are. Where are we? So we figured out what delta x was. That's where we started. Then we figured out what xi is. Did we? Yes. Xi is 1 plus 2 over n times I. And then finally, we can just put this all together. So what's this look like now? Limit n goes infinity. Sum I equals 1 to n. F of xi is going to be, what do I do with this to get that?
Put it into the function.
Yeah, of course I erased it. Just in time to get to that step. What was the function again? Thank you. So what's f of xi going to be then? Take this and plug it in. Now, does that look nice?
No.
Was it hard to make? No. Right? So as long as both of those statements are no, it's not nearly as bad as it could have been. That was not difficult to do. I just took this expression and plugged it in. Didn't even think. Just put it wherever I saw x. Didn't even think. Thankfully, this problem says, do not go further than setting it up. Because today we're going to go further. I wouldn't want to go further with this one. This is disgusting. Right? Let me think. What else? Times delta x. And what's delta x? 2 over n. So you can already see a little bit of simplification you can do, but you can stop right there. That's set it up. And if you look at number 22 in the book, that's the exact opposite of this. They have a setup, and they want you to pull out what f of x is, and they want you to pull out what A and B are? Let me see. Blah, 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 blah. Oh, determine a region. Yeah, they want you to pull out what f of x is and pull out what A and B are. I like it. So number 22, for example. We're going to do a lot more of this today, by the way. Number 22's got this thing going on. First off, can anybody tell me what delta x must be?
5 plus, 2 over n.
2 over n. They just put it in the front. Ooh, look at them. Right? And you see also, you can see it here. Because what is this? This is going to be the function evaluated. So what do you think the function is? And what do you think this is?
It's 1, it's x times.
So in general, it's a plus delta xi. Right? Can you see that form? And we knew delta x was 2 over n, because that's the good thing that's on the outside. That's delta x. What must f of x be? I'm sorry. No.
1 plus, no, 5 plus.
This is a plus delta xi. So what's a?
5.
Oh, so x is
5. That's crazy. So what's f of x? What did I plug a plus delta xi into?
x to the 10th.
X to the 10th. Beautiful. I plugged this into there. So they just immediately give you a backwards one. Can you set it up? If somebody else set it up, can you figure out what the hell it must have been, the f and so forth? I like that. Look at it from both directions. I would like that. Can somebody tell me what b is?
If it starts at 5.
If it's 1.
A is 5, so b must be 7. Of course it, well, what's that?
Yeah, 5 plus 2
That's b minus a.
over n, yeah.
B minus a. So the b must be 7, so that 7 minus 5 gives you 2. Alright, let me make sure. If you understand what we did over there a bit, then you understand what just now happened. Yes, ma'am?
How did you know A equals 5?
Because of this right here. Alright, so I have to see this, and xi is a plus delta x times I. Alright, maybe. Again, we're going to do several more of these today. This I like this as a jumping off point. So section 5.1, they have you set it up. Section 5.2, they have you set it up and then actually work it out. So we're going to do that today. So the thing after today's lesson, if you haven't done all of section 5.1 yet, some of that will be easier to do. So anything else from 5.1 or 4.9? Or did I skip over something? Did you have a question? You're good?
Yeah, really good.
All right. So where I want to start, hopefully, I think you guys, even if you don't totally understand what it would take, I think you understand that if I try to go further with this one, for example, that would be remarkably disgusting. So I really want to make an analogy between where we were before we learned the shortcuts to derivatives. Do you remember this? Let me pull all this away. So before we learned all the shortcuts, what was the only way we had to do a derivative? And I'm being real. I'm taking a big risk here because some of you guys are going to turn off the minute I go back in time. You're going to no. But no, derivatives, I can't touch those. I can't unless it's a final exam and I force you to use the limit definition. I'm not going to suddenly make you do that and nowhere in the middle of everything. But just to remind you guys, we had to use this thing, right? Yeah. We use this one, for example, but there's a whole other setup. I don't know if you guys, I think I pointed this out, but there are several functions that it's basically impossible to do this with. And if you use L'Hopital's to do this, to figure out some function's derivative, isn't that basically cheating? Aren't you using the fact that derivative is something to figure out what the thing's derivative is? I think that's known as cheating, right? But what I'm trying to get you to understand is, that last one we did, I would never do it that way. I would use the shortcut that we're eventually going to determine based on observations we make. Here it was a little more direct. We made several observations. We first did this one, of course. We figured out that guy's derivative formula based on observations we made as to what it does, the various powers. We saw what happened. You guys kind of remember that? Remember that? This happened. Okay. So, what we want to do is the same kind of thing for integrals, for these antiderivatives. We first have to look at the real nuts and bolts of how to find the area under a curve. Then I have to marry those with something we've already done, a shortcut, right? Because this, thank God, we're not going to do forever. It's sort of our limits before you learn derivatives step in the class. So this is going to be our integrals before you learn the shortcuts, right? So just deal with it until we get there for the shortcuts. So let me see. So section 5.2. Let's come up with an easier function to look at and try to redo what we just did so that we can actually figure it out. I know, we'll use, well, let's see. Let's just use the one I've got on my handout. Well, we'll use a slightly different one. Let's see. Sure, Jeff. This one. So it took a lot of thinking. Let's just leave it, Jeff. It's all right. Well, let's make it, all right, there. All right, I'll leave it alone. So now what I want to do is I want to do the same. I want to figure out the exact area under f of x from a equals what, Jeff? A equals 1 to e equals, sure, from 1 to 3. So I want to figure out that exact area. All right, and I think I already showed you how the calculator can do it for you. This is nice for the calculator. The calculator is not taking this course, though. So let's see if we can do this. And I put under in quotes. I'm going to take the quotes out pretty soon. But when I say under, I made this point last time. I don't mean under forever under, or else every integral would be infinite. I mean it stops at the x-axis. Right? So for an integral of a function that's below the x-axis, it's actually above. It's always between the x and the function. So if it's up here, this is the area I'm talking about. If it's down here, this is the area I'm talking about. So areas could actually cancel each other. If you had like a sine, if it did area of sine from negative pi to pi, that would cancel each other out. Do you guys see that? Because the area and the area, those areas would cancel each other out. I like it. Cool. Cool. Okay. So here's the steps. The first thing I want to figure out, hopefully this makes sense from what we did just a minute ago, was I need to figure out what delta x is.
Well, 3 minus 1 is 2.
And remind you guys, we're eventually going to use this guy. Come up here. Get out. Do it, Paris. Yeah, 3 minus 1 is 2. That's crazy. So we have this thing going on today. That's kind of a theme. And then immediately, what could I figure out after that? xi. So this is b minus a over n. xi is a plus delta x times I. Some very nice formulas just to plug stuff in. Let me make this like this so it's a little bit clearer. It's not 2 xi's in there. xi is a plus I delta x. So it's a. 1. Plus I times 2 over n, 11. Yeah, so step 1. Step 1 is to create your building blocks. Your building blocks are delta x and xi. That's what goes into building this thing. Step 2, remarkably enough, is figure out what the hell f of xi is. You know what xi is now. What the hell is f of xi? What's that going to be?
3 times 1 plus I, 2.
That's insane. So you take that and you plug it in. And what do you get?
3 plus 6i over n minus 1, so it's 2 plus 6i over n.
So that's f of xi. So I've got this. Oop, get out of here. I've got this, which actually goes into building this. All right, let me stop there for a second. All right, so this is the more general analog to the concrete problems we did the other day, where I said using 4 rectangles, using 6 rectangles. That is a very simple problem about figuring out the areas, adding them up. Ooh, big deal. This is more real math. This is not just computation. This is actually conceptual, right? There's some abstractness going on here. I love it. I would. So if I put all this stuff together, what do I get? So I put in there f of xi and delta x.
2 over n.
Now tell me this is very important. Which variable does the sum care about? Sort of, and let me be more specific. Which variable is tied to the sum? Well, which variable is tied to the limit? Let's see, that should be the easy one. N. N is tied to the limit. N is going to infinity. So whatever n is, that just happens to be the number up here. So the sum isn't tied to it. The sum is dependent on I. I is changing for the sum. What does I do? I is 1, and then it's 2, and then it's 3, up to n. So I is controlling the sum. I is controlling the sum. I know half grammar. Right, so I is controlling the sum. And what's controlled by the limit? N. So what's my point with that? I can take out of a sum, I can take n out all day long. Because I is the sum variable. N is just a freaking number. So I can take it out. I'm going to take n out here. So let's go a couple steps further. What's the first very obvious thing you can do there?
Distribute.
No way. So distribute. So I get 4 over n plus okay. Yeah, that's ground shaking. But now, and just to make this really clear, this is a good idea in general, just so you know how far the sum goes. The sum is over all that whole expression. Let me take this away here. I got a little handout that's got the steps on it. It's got a worked out example. So it's going to help you with your notes. Alright. So let me go one step further, and then you'll start to see maybe what I mean. So if I split this sum up, like this. Start to have a little motivation as to what has to come next. Oh, that's right. That's right. So, what did I just say? What can I take out of here? Yeah, I can take the 1 over n out. I can take the 4 out too, but I want to kind of leave something in there to add up. And the same thing over here, what can come out of there? And this time I'll go ahead and take the 12 out. 12 over n squared. And what's left inside? I really, really want you to understand. Why can I not take that I out? Because I actually only exists in here. It can't come out of there. Right? Oh God, I had a geeky moment where I'm like going to say something about the holodeck and people coming off the moon just disappearing and shit. No? Nobody's with me on that? Little holodeck characters? No? Alright, that's a little too geeky. Thank you. Alright, I have my geeks out there that I look at to understand where I'm coming from. For the rest of you guys, I'm sorry. You can't take an I out because I is set up by the sum. It can't exist outside of there. And I can't take the n's out of the limit because the limit's telling me what n does. Yes?
Why didn't you take the 4 out?
I could, but it would have been a 1 there, and it's just kind of silly. So, I could have done that.
Okay.
But I want to make a point right now, a larger point about any number that's left in here. Right? And the 12 I felt comfortable because this is really what we got to focus on now, is that. So, hopefully you guys understand that if my original formula would have been parabolic, would have been quadratic, I would have had an I squared here. Right? If it was cubic, I would have had an I cubed here possibly, and then there's several different possibilities. How are we doing? So I need to figure out, this should be easy. Could somebody please tell me what this is?
4.
No. Because what is it saying? It's saying add up 4 n times. So let's do this. Let's have a little sidebar. Let's pretend like we're in law school or something. Okay. Here we go. You ready? This is some summation notation practice. Let's do this. Sorry. Start off with that. All right. What does that mean?
Count of
Sum.
4.
Can you write? So what's I at first? 1. And then, of course, it's the sum. And then what's I next?
2.
And then what's I next?
3.
And then what's I next?
4.
Okay, and so that's that sum. 10. Right? Yes. Cool. Alright, just make sure we're all... I want to make sure everybody remembers what summation notation tells you. Now this sort of becomes silly now. You're going to add 4 to itself how many times? You're going to add 4 to itself how many times? 4 times. Isn't that the definition of multiplication? Right? So in general, the sum equals 1 to n of any constant
Is it times the end of?
is c times n. Yes, don't make a different n, Jeff. Just make it. Do you guys see that? Do you guys understand why that's true? It's very simple. You gotta love it. Alright? So we gotta figure out, what do we have to figure out now? Now I have a general formula for this. That's nice. But now I gotta figure out a general formula for this. Because that is right there. Stupid little thing. I got to figure out a general formula for that. Hopefully dependent on n, because then this is telling me what n's doing. Let that sink in. And this is actually something that I teach my 120 students. It comes up sometimes in other classes. It sort of can come up anywhere. It's something that Gauss did. I can't remember if we touched on this yet or not. If we did this in here. Something Gauss did back when he was 10. It was an urban legend in math. You guys know this urban legend? It would make a very lame movie because it was just. So let me give you an example. Get out of here, good writer person.
Hidden man.
That Kevin.
Easter egg.
So watch this. You ready? If I start at 1, and why is this important to start at 1? Because my summations normally start at 1. So it's kind of good to build off of there. And let's just take 1, 2, 3 up to 100. We write a couple more things out just to be like that. Everybody with me? So that's a sequence of numbers. Now let's say I want to add up those numbers. Right, so the urban legend was the class is going crazy. The teacher said, everybody sit down. You add up all the numbers from one. I don't know what country that person is. It's supposed to be German. But I can't do it. I don't know what that's not existing. And so Gauss was a smart kid, a little smart ass too. And he does it in like 10 seconds and brings the answer up to the teacher. And the teacher's like, what the hell? So the teacher goes, 1 plus 2 is 3 plus 3 is 6 plus 4 is 10, and just does it all the way to 100. He says, you got the right answer. How the hell did you do it? So what Gauss saw was 1 plus 100 is, 2 plus 99 is, 3 plus 98 is, and how many of those are there going to be? 50. There's going to be n divided by 2. In this case, 100 divided by 2 pairs that are all 1 plus n, because the first number plus the last number. You with me? So that is what the sum of I equals 1 to n of I is. That's what it is. Because that's basically what we just did, right? If it was 1 to 100, it would be this. And the funny thing is, what's that come out to 50 times 101 is? What's 50 times 101? 50-50. I love that. The sum of the numbers from 1 to 100, the integers, from 1 to 100 is 50-50. You gotta love that in a way. You just gotta love it. And if you don't, That's too bad for you. So this is the formula for I. So what about, let's just take a second while we have it up here. What about I squared? What if that shows up somewhere? You would just blindly hope it's this squared and you would be very wrong.
Is this like the K?
Yes, good. We're not going to do that in this class. We normally, and that's too bad. I wish we had time in this class. But there's something called, do you know what it's called, the proof method you're talking about? It's called mathematical induction. It's one of the kick-ass, coolest things. There's just not enough time for us to do it here. I'll let it go. I was about to launch into it. What Jeff just said, there's not enough time to do it. It's just such an awesome, powerful, almost too easy to believe as a student thing. And it just takes a little bit of acceptance. It's too bad for you guys. All right. But let's get a feel for this. Let's get a feel for what's going on here possibly. So if I had I equals 1 to 3 of I squared, what would that look like? What's the first element? 1 plus. Because now I is 2 next, so 2 squared is 4. I is 3 next, so 3 squared is 9. And I get 14. Why are you guys looking at me like I'm crazy? You guys understand what's going on here? Saying, let I go from 1 to 3 and add up what I squared is. So I squared is first, 1 squared is 1. Then it's 2 squared is 4. Then it's 3 squared is 9. And then you add them up. That's the idea. So what would sum I equals 1 to 3 of I cubed be? 8 plus 27, which happens to be 36. All right. So this one I'm not going to prove, unfortunately, because it either takes some weirdness or some math induction would make it really easy to do, but we don't know math induction. So here's what it is. Let me put this one here because we need this one immediately. We'll come back to this. Make some room here. So this one is this. Did I get everybody in there? No, I think there's no N in there. Yes. Yes, John. Cool. Now let's check it. Let's check it. We can't prove it, but we can check to see if we believe it. What would N be here in the specific one we did? What's N? I equals 1, 2, 3. I don't know. You guys here? You guys here? Or was that too easy a question? Sometimes I ask too easy of a question, nobody else to say, because they're like, it's too easy, man. Just give me something in the middle, because if it's too hard, I'm going to say shit, because I won't know. Alright, so I don't know what's in the middle. So if N is 3, I should get 14 from this formula, should I not?
Yes.
Because it's supposed to be the same damn thing. So let's see, if N is 3, what's this? 3 times 4 times 7 over 6. 12 divided by 6 is 2 times 7 is boom. Or not. Alright, so that's what it is for I squared. I've got all these on a little handout also, and they're in the book.
So these are just something we have to memorize. We don't know how to build that.
I'll give these to you. I'll be really nice. What about I cubed? So the sum of I cubed, n equals 1 to n. Yeah, I equals 1 to n. That's going to be interesting. It's going to be the same thing, and this is what you thought the other one was going to be. Yeah. Well, this is what you thought I squared was going to be, because it's like the square of what I is. What I do be. My grammar is awesome with the I's. Alright, so let's check it out. If n is 3, what's this becoming here? 3 times 4 divided by 2 squared. 6 squared.
36.
Holy shit. Alright, good. Alright, so that's not a proof. It's definitely not a proof, because maybe that's the only number it works for. But these are true, and they can be proven by a method called math induction. They're actually proven in Appendix I think this one is proven in Appendix E in the book, if you want to look at what that looks like. Okay, so let's come back to here. So as all a little side note. Okay, how are we doing so far? Are we decent? Okay. So coming back to this. Now, so tell me what this is. That kicks ass. Now this is 12 over n squared times, now what's this? Alright.
Why did you do that? It's just I by itself.
Well, I'm sorry, what? What is the sum of I from 1 to n? It's n times n plus 1 over 2. It's what Gauss did. It's the formula that Gauss came up with. I like it. The I squared is more disgusting, and the I cubed is actually that thing squared, which is really weird that it comes out like that, but oh well. Math does that sometimes. How are we doing so far?
More good.
So the level of computation required here, the only place it's difficult is in the proof of what we're just going to use. So it's nowhere difficult. Nowhere is the level of computation difficult. I'm not saying that this problem you should be able to do it right away. It's just got a lot of stuff we're not used to. But the level of computation is low. Can somebody help me out? What's this? 4. The limit of 4 is 4. Now what can I do here? Can somebody see what I can do here? Because n is going to infinity. Yeah, this over this goes to what? What's the power up here? Squared, and the power down there is squared. So the limit should go to the ratio of the coefficients. We're going to use old pre-calc stuff. Holy shit, pre-calc was really useful. So this limit is 1. You guys see that?
Yeah.
It's 1n squared plus who cares? Over n squared, the limit's going to be 1. So what's this become? So let me do this again here. So here I get, is everybody cool with this? This is just 4.
Oh yeah, that's 4.
Now watch, if I rewrite this a little bit, can I replace the 2 and the n squared? Of course I can, because they're both on the bottom. I'm going to distribute this. Get out of there, 2. Pre-calc, what's the limit? 1 over 1. 1, so then you get 10. Now somebody help me out, what's a 10 mean? What's that? What's 10? 10 is what? Go further back. Go to the original problem. What did we just discover? What was the original problem? Area. Good. So 10 is the area under f of x equal to 3x from 1 to 3. Right? That was what set up this whole problem, wasn't it? So when we get to the end of this, we're going to find an area under a function. That's what this does. This finds the area under the function. Why does it do that? Because it makes rectangles, gets their areas because it's easy and adds them up. Just happens to use an infinite number of rectangles. And that's why it's a little more difficult than if we just had like 6 rectangles. A little bit more difficult to go to an infinite number of rectangles. Right? But it's doing the exact same thing we did the other day. It's doing the same thing. It's just that how off is it? Is there any error?
No.
It's perfect. Because what did we crank the resolution up to?
Infinity.
Infinite resolution. Dude. Alright? If you had a TV that had that, I think your eyes would melt. So let's not go there. Alright? Infinite resolution.
You probably wouldn't be able to see.
No, everything else would look like shit.
It would just be your eyes.
It'd be like South Park where it looks like shit. Alright. Come back, Jeff. That's enough of that silly shit. So what I want to do is something geometric here. I want to still look at this function again. Can you guys graph that function for me very, very remarkably fast? Graph that function for me. Not in your calculator. Don't graph in your calculator. Good Lord, man.
By hand. Well, up
Oh, I'm sorry, it was 3x minus 1, my bad.
Yeah.
Oh, 3x
I
minus
was-
1.
That's all right.
3x for 1.
So at 1, it's where? At 2. At 3, it's where? At 8. All right, that's a hard one to craft. Let's see. Yes, I am being a dork to you. Here's a line, right? It's a straight line. So to find that area geometrically, what shapes do I have here?
It's a
Triangle, and I have a rectangle. What's the area of the rectangle?
2,
3 times 3. I mean, 2 times 2, sorry.
4.
4. And then this, again, this is still 2 here, right? This is 2. And what's the height? 6. So what's the area of the triangle?
6.
Yeah, half 12 is 6. So what's 6 plus 4 for the area of the whole thing?
Oh my
10.
gosh.
Now, of course it is. The minute I make this parabolic or some shit, do you want to do it this way? You can't. I don't care if you want to. You can't. So why do we pick these kind of problems to do first? Because they're easier, and I have multiple ways to do it by hand. So I can make you really buy into this working. This totally works. Of course it does. But I want you to see it. You can see it happen. You can see it. This is 10. This area is 10. There's no question. That's what we got doing this. If we would have got something else doing that, we could throw it out and forget about it. All right? So tell everybody calculus doesn't work. Really? Shit. Your phones would stop working. Trust me. Calculus doesn't work. Everything, nothing works. Okay. All right. Let me give you this handout. Let you absorb what's on here. Absorb. Chapter 4.
The Travis. Yeah.
How you doing? You're doing good. So what I want you guys to do right now is, now that I've gone over a simple example, and there's a simple example that you can look at, I'm going to give you a little bit harder problem to do on your own.
Oh.
Yay, teacher. This is not anything I'm going to grade, so who gives a shit, right? Let me let you try it out on your own so I can see where you have trouble before you have to actually do something you're graded on. See how that works? It's crazy. So do everything we just did. Find the area under x squared. Yeah. From x equals 1 to x equals, well, let's just stick it like that. Let's keep the 2 over n theme alive. So you've got the steps. You've got the steps. This is x squared, so some of the work is going to be a little bit weirder. It's fundamentally the same thing.